Welcome, code aficionados and digital daredevils, to a podcast that's about to dive deep into the fascinating world of WebAssembly. WebAssembly, or WASM for the initiated, is revolutionizing modern engineering, pushing the boundaries of what developers can do. It's like a secret portal connecting your code to the digital cosmos. On this show, our hosts, Joel Moses, Oscar Spencer, and Matthew Yakabuchi, will be your guides to this virtual dimension, decoding the mysteries and unveiling the endless possibilities. So strap in for a bite sized adventure as we take off with WebAssembly Unleashed.
All right, thank you, Tabitha, and welcome to WebAssembly Unleashed, your source for news and views about the world of WebAssembly. I'm your host, Joel Moses. Alongside me, as always, my fellow WebAssembly obsessives, Oscar Spencer and Matt Yakabuchi. As you know, here on WebAssembly Unleashed, we always provide perspective on proposals, changes, updates, and community meetings, what they mean to the WASM standard, and we also, along the way, we talk some good trash about the community we all love. I'm super excited about our WASM community guest today. We're going to get to that in a second. Let me introduce my compadres, Oscar and Matt. Welcome, guys. Now, in the interest of full disclosure, I just want to say Matt has moved on from being a day-to-day colleague with Oscar and myself, but is still a WebAssembly enthusiast and has
Yes.
graciously agreed to come hang out with us on a regular basis. Matt is taking his time to indulge in one of his passion projects. And what is that, Matt?
Among other things,
Among
but
other
I've
things.
gotten some beekeeping beehives set up, and so I've got two queens going right now. We are building the colony and just trying to keep predators away. That's my main focus right now. Yeah.
That's cool. I would imagine wrangling bees is not all that different than participating in open standards initiatives, in my experience. So I'm sure you're going to nail that one. Oscar, I hear we have some action coming up in the community.
Yes, indeed. So as we are recording right now, next week is the in-person WebAssembly community, well, W3C WebAssembly community group meeting, which is exciting. Always amazing to see everyone in person and chat through all the fun new specifications that are going. Actually, I believe on the agenda, I think 4 different proposals we're voting to go to phase 4. So it's going to be an action-packed CG meeting.
That's
Four
going
in
to be
one,
wild.
4 in 1 meeting. Will the meeting ever end? I don't
It's 2
know.
days long, so
Okay,
I think we can get through it.
it's good to
So that's
cap things like that.
yeah.
That's great.
Yeah, that's exciting. And one other thing I'll throw out, and this is my personal agenda, but the latest major version of WASM Time has tail calls enabled by default. And that
That's
makes
sweet.
me incredibly excited. Not that I'm a functional programming language person or a person that works on a functional programming language for WebAssembly, but I may have been sick and tired of people trying to run a program with WASM Time being, it says that tail calls aren't enabled. Like, just turn them
Okay.
on. Like,
So now it is.
And now it is. So I won't get anyone bothering me about that anymore. So,
Well, that's good. That's
yeah.
good. It's definitely all about Oscar's time. Trust me on
Exactly.
this one.
Yes, correct.
Now it's time to introduce our super special guest. I want to bring on board Luke Wagner, distinguished engineer in the office of the CTO at Fastly, co-chair of the W3C WebAssembly group, Mozilla alum of the SpiderMonkey JavaScript effort, and co-creator alongside Alon Zakai and David Herman of ASM.js. Now that's the proto WebAssembly engine that set a lot of our imaginations ablaze when we first saw it and played with it in, what was it, 2013, 2014?
Yeah, that's right. Yeah,
That's
2013.
awesome. Luke, welcome, and let's jump right into it. So
Yeah, thanks for having
let's.
Welcome.
I do
Hello.
want to kind of dig into the history a little bit around ASM.js because I'm just sort of curious about this. Now, at the time, 2012, 2013, Google was out there pushing for NACL, like native client for native speed, and watching their progress on that, and then comparing it to the early version of ASM.js's approach just kind of blew my mind. I remember reading about it in the FAQ and on Badass JavaScript and other places, and thought it was a particularly novel, if somewhat strange approach for native execution.
Truly.
Can you describe for me what that crazy water cooler conversation at Mozilla was like that led to ASM.js?
Yeah. Well, the big question was, should we do native clients? And remember, there was two subtly different, but importantly different ones. There was native client, which shipped actual native machine code to the browser that was carefully sandboxed.
Right.
And then people were like, "What? We're going to ship x86 on the web? Like we're going to lock in these architectures forever?" And so they got all that feedback. And they're like, V2 portable native clients, and what we're going to ship over the wire is LVMIR. And so
Right.
that means what has to be part of the browser now, trusted computing base, is the whole LVM compiler, which actually they did a pretty good job mitigating by locking that down big time. But ultimately, you have a LVM compiler inside your browser now, compiling it to the machine code. So there's portable native client, which made the
Right.
engineering lift even bigger. And so the big question facing the Mozilla leadership at the time, because I was a pretty junior engineer, was, do we do portable native clients? And there was a lot of hand wringing, a lot of arguments on Hacker News, and so got our kind of marching orders from the various leaders to like, can we find another way? Should we do? There was WebCL based on OpenCL,
Mm-hmm.
Mhm.
optimize JS harder, just keep jitting, do better. There
More JIT,
was
more JIT, more
more
JIT.
just be fancier, just more magic, just be sufficiently smart, please, y'all. And so there was all these different approaches. And so one thing that kind of happened at this time that kind of blew everyone's minds, including mine, was Mscripton, made
Oh
by
yeah.
my colleague
Yeah.
Alon Zakai.
Alone.
Before we did anything special for it in the browser, it was just getting faster and faster as he kind of kept tweaking the output, finding that sweet spot. JITs got better. Typed arrays came on the scene. He used typed arrays. Now all of a sudden, we're emitting code that's faster than handwritten code,
It's
because
cool.
it's
Mhm.
just using typed array loads and stores, which are like actually compiled pretty well by the JITs of
Mm-hmm.
the time. And so we're like, oh wow, Mscripton, you can totally compile like big code bases with this thing, and people were. And then the bug reports would come to me, and they're like, here's my 10 megabyte blob of JavaScript. It crashes in the middle, or the scientist
Fun.
flickers. Figure it
Good
out.
time.
And you're like, oh my god, how do I even? And so there was this like, wow, this is amazing, but like, how could we like lean into this and
Right.
like fix the remaining warts and say like, what's the least amount of work we could do? Because we're looking at like the Google Native client team had done huge amounts of work, but it was like I don't know,
Massive.
roughly 10-ish person team over 5 to 10 years. I don't
Right.
know. I'm
Wow.
probably off on each of those, but huge effort. Now, granted, we could borrow a lot of their work, but still very large effort. And so the whole gist of ASM.js was like reuse the JS parser, reuse the JS JIT backend, just
Yeah.
add like a little link in between that's like we type checked, and then we went straight to this type specialized IR that we already have optimized in the backend. So the
Gotcha.
part in the middle is usually where the JIT goes wrong, where it's like, oh, I didn't pattern match on the right, thing. I didn't find the right type information, or just you spend a lot of time in the middle going through loops of like profile and, optimize,
Mm-hmm.
de-optimize, profile some more, and reach that fixed point. So like skip all the middle junk and just go straight from, we parsed it straight into the IR, and
Right.
surprisingly, it worked. It was like roughly like 1.5 engineers got this working in like half a year, and then we got to that Unreal demo you're probably thinking
Yeah.
about,
I
and that
am.
we
I am.
debuted at GDC, and with FX great support, and everyone was like, "Oh my gosh, you could do that!"
Explosion. It was
Yeah,
amazing. Yeah, it,
yeah.
it very much felt like, knowing especially how much work was going on in native client, it felt kind of like the emergence of the Rebel Alliance. You know what I mean?
It
It
felt
was
like
kind of
that
cool.
too.
So continuing on from that into the current day, arguably we're inside a massive uptake of WebAssembly. I mean, arguably, I just saw a blog post from Microsoft about embedding into Visual Studio
Yeah.
for the component model, right? And I,
hmm
these are things I never thought I would see. What excites you right now about what's going on with WebAssembly?
Oh, just the breadth of things people are doing with it. Like every new time WASM gets embedded in a new context, I'm like, yes, that's that. Because the whole point of this thing is it's embeddable, and
Hmm.
in
Yeah,
what in
it's like,
everything.
oh yeah, it's the point.
Yeah,
Yeah.
right. And each one kind of gives us new use cases, and that justifies some of this effort trying to factor out all this hard problems, saying let's solve some of these problems in a way that doesn't care what platform I'm on, that doesn't assume that I'm just on a traditional POSIX, system. We want to be
Hmm.
able to support that type of workload, but also radically different workloads. And so
Right.
the more diverse workloads we see in compute environments, the more it helps build this, the justification for working on this common set of standards and
Yeah.
machinery.
And all kind of rooted in that ISA independence in the early from the early days of ASM.js. It's a
That's right.
fantastic story. Now, I want to get into this. You gave a great presentation at WASM.io recently on what I'd call extending the superpowers of the component model with a path to async and streams. And as a person who personally has struggled with coding for like composability in the face of massive concurrency problems in at scale handling of like network streams for HTTP and
Mhm.
Quick, that's been a really frustrating problem to tackle in early WebAssembly efforts. And I want to bring in Oscar here. Oscar, I know you've spent a lot of time working on this exact thing in the community, and I know you have lots you want to surface on the topic. So over to you.
Yeah, absolutely. So The really exciting thing, just to catch everyone up, preview 2 is simply preview 1. We learned a whole bunch, like how people actually want to use this. So maybe a handful of things that were missing, but shockingly not as much as you'd think. And all rebased on the component model, which is super sweet. And so the whole idea behind preview 3 is we're going to add async and streams.
Yeah.
So everyone is very scared around the idea of async and where it's really going to go, right? Because this can fundamentally change how WebAssembly works, how people think about it. So, Luke, can you just first tell us what's the general concept for how async might even work in the component model?
Yeah, well, so I guess to start with the problem statement of what do we want to do here, which is I when I call a function to do some task, I don't want to have to wait for it to completely finish before I start the next one, right? That's sync, not a. And so fundamentally, I want to be able to have multiple operations overlapping. And then furthermore, once with this one operation, if it's sending me back bytes, well, I don't want to wait to get all the bytes all at once and all in my memory all at once. I want to chop up those bytes and get them as they come over the wire stream. So that's
Yeah.
and streams. So I think the basic problem is how do we do asynchronous function calls, and how do we even further, stream just the, as I'm passing parameters out or I'm getting things back, how do I further incrementalize? And that's where streams come in. And
Mhm.
how do we do that in a way that does not require the developer to handwrite a bunch of low-level grungy concurrency code? Let's let them use the features that in their programming language that have a huge amount of work to try to make async as easy as it can be, which is still not easy, but easier than
Mhm.
hand rolling your own select loop or C
Right.
pull. And how do we let them use their language features? And lastly, how do we have, if I have two components and they're both doing logically just implementing an async function, can I just have them compose and just one exports the function, the other one imports it? Can
Mhm.
it seems like I should be able to do? I can do it in sync, and I lose this entirely now with async. Can we regain that in preview 3?
Yeah. So I think the big question then is that, all right, we got some sync functions and maybe we're going to have some async functions. Does this split? Does this split WebAssembly, right? We've seen some ecosystems where, okay, I can only use this set of libraries because these are the ones that are async, like these ones return promises or whatever, and
Right.
these ones are all callbacks or whatnot. So, how are we thinking through, that exact problem of can I use these two things together? Is it going to work? If you hide it away from me and magically do it, is it going to be performant? What are folks thinking about these?
Yeah, and that's a really important problem. And I guess people have probably seen this blog post, "What color is your function?" that kind of characterizes it in the most general form. And when you read it, you're like, "Yeah, I don't want to do that. I don't want to have to,
Mhm.
partition all my functions, and these ones are over here, and they can't call this one." And I think some of the languages that have done that do it for just a hard reality of they have to be very low level. They can't have a runtime doing interesting stuff below
Mhm.
because they're implementing that runtime. So we
Yeah.
can't just assume we've got green threads and we can mess with the stack because maybe we really can't. And so I think Rust is very well justified, for example, in not not saying in having some of the current function coloring. But we can look at, say, what Java's done with Loom, which they did a huge amount of work for. And I'm seeing just constantly people really happy with the result, which is, hey, instead of having to do all my own thread pooling and do async await manually in user space and come up with libraries and all these things, what if the primitive we give to developers is these kind of lightweight green threads that are M to N, multiplexed over the OS threads by the runtime? Now I can just spawn these functions and they don't have to, be async or have a color. They can just do their work, block on what they want to block. And, if there's more work progress to be made in another green thread, the runtime will just switch to it. So that's kind of an example of an intuition of like they have, that approach, the stackful coroutine approach, can avoid function coloring.
Mhm.
And so that's one kind of intuition is let's just have functions that are async and they can block. And when I call an async function, I can say if you block, hand control flow back to me so I can keep making progress on something else. And we're going to say that we're not even going to have to like have that in the function type. We're to say like functions by default can block. Maybe we have a way to opt out of it and say no, this is a function that promises it'll never block because it's some trivial getter. Don't even bother with the async code gen. It's just we're ruling it out, but that's not the default because in general things can block, and I need to be able to handle that.
Right.
And so then we say, okay, but there's lots of different language mechanisms for how to express this. Like the way you do this in Go is very different than in JavaScript, is very different than C# and all these languages. So how do we not just force them all to like have the exact same language feature, or assume that they do and then to be disappointed. And it's roughly by saying, let's have a low-level ABI that's kind of like an operating system would give you for starting work, getting back a handle to work in progress, being able to like wait on progress on any of these tasks in progress. Let's give a low-level ABI that faces the inside of the components and that my compiler, my toolchain can target and bind to. And then and that way different language features can bind to that in their own bespoke way. And you're like, well, already if you're any of these languages with an async feature, you have to bind to the async mechanisms of different operating systems. You have to do epoll things or IOU ring things or overlapped IO things or KQ things or so many different things. So there's already this some sense of like, well, at the very lowest levels of your async framework, you're going to have to bind to some sort of OS ABI anyways. And let's just be one more that that is really good for WASM and is tailored for the constraints of WASM. So we'll let the languages kind of bind to that. And so we have to have the high level semantics of the component model says like, this is an async function. Here's kind of the basic rules you can assume. This is the game we're playing. And then this low level ABI that lets you bind your language to it.
And it sounds like you still keep this property of WebAssembly where everything is decoupled, right? Where like WebAssembly is still opaque to the user. Like I'm just going to write Go code or I'm just going to write async Python code and boom, it happens. And so like there's no decorators. What I started to get scared of is like, oh well, put £sign WASM in here to get some async behavior, but we're not going to go in that direction.
Yeah, or say, well, these are the Python style coroutines, and these are the JavaScript style async functions return promises. Yeah, that sort of language. You kind of want to not let the language specific details kind of see through that language agnostic interface.
Yeah, and I think thinking through, how this can look in practice, definitely calling between separate components. I can totally see, like, if I have maybe 5 different components that I all need work done, I can say component 1, start this work. Component 2, here's some other work. Oh, my work in component 1's done, and like that can probably be fine. For the case for a single component, it starts to get a little bit trickier, right? Because I might ask that component, hey, do this work, and ask it to do some different work. And depending on how it's organized, its internal structure, it might be able to do those 2 bits of work at the same time, maybe not. And in the maybe not case, that's where I think things are a little bit more interesting. So if I say, hey, component, launch these 2 tasks for me and give me the answers, maybe it's got linear memory inside. It's not using like, I don't know, a mutex or something that makes it able to handle that. So are we just saying that's fine, or do we have ideas around that?
That's a great question. This gets to some of the challenges with the beautiful, perhaps, otherwise idealistic picture that I just painted, is what happens. There's a bunch of code that's fundamentally not reentrant, right? It assumes it gets called once, it runs to completion, and if we attempt to just start another async task, it'll feel like a signal handler, right? You're running this code and all of a sudden, bam, you're running this other code and it's just interleaving in a way that you didn't expect. Definitely that'll break global invariance. So what we need to recognize is that some code is fundamentally synchronous in its implementation. And so somehow we have to say, what happens to that code when it gets used on the other side, when the other side is async code and is attempting to call it, and start multiple async tasks. And the kind of neat observation we can make is, first of all, even in a fully async, even when I'm writing in a fully async languages, if I'm spawning a whole bunch of async tasks in your component, each one's consuming some memory, copy its arguments to represent its task structure. If I keep spamming you with tasks before they get to finish, which can easily happen, I'll loom you. And so we need the ability to express this universal concept of back pressure. I need to be able to say, hey, I've got too much going on. Hold on. Don't even start anymore. Let me finish some other stuff. So this is the essence of back pressure. And the interesting thing that was not initially obvious was just the act of calling an export needs to be a point where I can exert back pressure. Because if I let it just happen, I can get overwhelmed and not have any attempt to say stop. If I'm already running and you've already allocated memory in my linear memory before I've got to say stop, it's too late. I've already zoomed. So we need the ability at the boundary for the component model to kind of exert some back pressure. Now, the caller now needs to say, when I make an async call, already it cannot finish. That's the whole point of async. But now we need to say there's a kind of different states it can be in. One is like, and it didn't even start. The parameters that you're trying to pass, they haven't even been copied out of my memory because the other side's not ready to receive them. So the first state I can be in is it hasn't even started. And then it can advance the state and say, okay, it started. I've read your parameters, but I'm still working on your results. And then after that state, here's the results. They're done. But actually, I'm finishing up. I'm doing some stuff I didn't want to put on the critical path. I'm doing that after. I'm finishing up, but I'm not yet done. But you can find out when I am. So we've got these 4 stages you advance through. But importantly, that I haven't yet even started. Keep those parameters ready for me. Is a state you can be in. And this can be a way to exert, so we have the ability to exert back pressure when you are fully async. Now we go back to our case of what do we do for the async component, the synchronous components, the C codes of the world that are just haven't been refactored to magically be async. What we can just say is this is code that has a concurrency limit of 1. I can start one task. If I try to start a second one, back pressure. When does the component model can do this automatically and say, I can see your sync. You've lifted with this function synchronously. You're not expecting to be interrupted. So as soon as I see a second export call, because I'm the component model, I'm in the middle anyways, I can exert back pressure. And as soon as the first task finishes by returning, I'll just queue the next one automatically. And from the caller's perspective, it's just a very low concurrency component. And so, it's sort of like a case you have to handle anyways. We're just dialing it all the way down to concurrency count 1.
Yeah. So can you see a future when, we're finally all publishing tons of components and we've got, here's some interface that my component expects, and we have different implementations that are now competing to satisfy that interface. Because if you use my component, it's able to actually do more asynchronous type stuff. Do you see that kind of future happening? I'm just excited for, everyone actually publishing components and just consuming them. That's just a magical world I'm excited for.
Yeah, but you can imagine there's this natural pressure of you start sync because it's easier to start with, and also maybe you ported some code that was written 20 years ago, and it's synchronous. Sure. But now your component's getting used a lot. Now there's a lot of interest. There's a lot of value in optimizing this. So now you've got you keep the interface the same, you refactor in place, and you unlock more concurrency for your callers. So I think you're right.
And so I know local hero Joel Dice has the ISIS-WASFA project, which stands for I sync, you sync, we all sync for async. And so for this project, I haven't gotten to play around with it yet or even see really the work that he's doing there. But what sort of work is happening where people are testing this stuff out to see if these ideas might actually come to fruition?
Yeah, Joel is indeed the hero here. So he started by basically saying, I'm not going to touch the actual component model. I'm just going to do some pretty clever as ifs, to use preview 2, as if I had async. And so he built that out. And what that allowed him to do is experiment with the guest code bindings. Like, can I make idiomatic looking async Rust kind of just work? And on the host side also. And he got that working, and not just individually, but 2 components composed and doing the hard cases of streaming in and streaming out and all the streams in all the directions. He got that working with ISIS-WASFA. And then he got that done surprisingly quickly. And then he rolled on to just actual adding the actual extending the component model with these features. So that's in, I believe, a public but personal branch, and now he's working on PRs to add them to WASM time behind an experimental flag, but actually so that anyone can actually just straight up start to play with this. And for this, again, he's gotten guest bindings working, host bindings working. We're writing high-level, safe async Rust, so you're in a radically safer position with a lot more language assistance than you were otherwise. And I'm just this week should be able to publish a PR that has the first chunk of the async proposal, which is up to but not adding streams and futures, but basically this ability to lift and lower a function asynchronously, and kind of written that in Python in this sort of Python specky code that's sort of like behave as if the Python did it. So I've been doing a lot of async Python in the last month. So hopefully posting that, and it should line up with the patches he's submitting. So we'll actually have not the whole spec, but the spec for a chunk of the feature that combines with actual upstream implementation stuff. So hopefully we're going to be advancing
fantastic.
that.
Yeah, this is so incredibly exciting. So we've talked a ton about async, and I think I just want to talk a little bit about streams. So we didn't get streams in preview 2, and essentially we have what is WASI.io is basically streams. And so I think one of the goals of streams is just to delete that interface so it just no longer exists. So are there going to be large changes versus that interface? Because I know for streams, I know one of the plans is to be able to have a stream of T, a stream of anything, which is really exciting. Just not by its actual things is really exciting. But so, and actually, I don't remember off the top of my head if WASI.io supports being able to do something like that. But are there any other major changes besides just trying to get rid of WASI.io?
Yeah, well, I guess you could say that is when the mission is accomplished, we'll be able to delete it because nobody will be using it. And stream of T will be one of the big things is we can, you can have streams of handles. You could have streams of streams of handles, So that is exciting. I think one of the big things that'll be improved is at the ABI level. Right now, the model of streams is kind of readiness based, and that often involves a certain amount of extra copying that has to happen. It's buffered in the host before it gets to be copied into the guest. And one of the big shifts with streams as a built-in part of the component model is that we can have a custom ABI for streams, just like we have for every type, that lets us register a pointer into our guest linear memory early when I'm saying, I would like to listen to the stream. In the future, when you're done writing to this, tell me, but the copy's already happened. And so in the limit, I can use IOU ring, I can do DMA transfers for my smart NICs directly into linear memory, skipping, going directly from the host, the kernel, or even the NIC, directly into our WASM linear memory. So that in certain scenarios will be a huge optimization.
So, like for WASI HTTP, instead of having a result of option of some type
That
Well,
terrible jump goes away.
Honestly, that enables a lot of things if you're wanting to touch on hardware acceleration, especially in SmartNICs, that's a way to do it right there at the compilation level, and not have to work with a lot of proprietary interfaces that some of these SmartNICs have for language bindings. That's incredibly exciting stuff. I love it, but I also just love streams because memory's not finite. It's definitely important to have that interface.
And in WASM, our unique value is give me a small slab of memory, and so I can have very high multi-tenancy. And so, we really have to be working in terms of small chunks.
That's really cool. For those that are curious about Luke's WASM.io presentation, we're posting a link to the deck in the video below. Please do watch it. You won't be disappointed. Especially watch it because it has a wonderful flex tape metaphor in it. Which I really liked. Luke, if I can, before we close up, I want to touch on some of the things you're doing now at Fastly. I personally was fascinated to watch kind of the graduation of the Terrarium project to become a central piece of Fastly's approach to compute management. And in doing that, you took a base technology for experimental use and you created a full service offering out of it. And that's not a terribly easy thing to get off the ground. I've got a couple of questions about that, and it relates to what you've done there. Fastly is and still it was and is famously attached to Varnish as a platform, and Varnish has its own opinionated way of offering programmability. Did you find it difficult to suggest an alternative approach to programmable compute?
Yeah. Well, so first of all, I can't take credit for all this hard work. A lot of it happened before I showed up at Fastly. Years before. In fact, this is part of why I went to Fastly was they're doing all this cool stuff with WASM, and that argument had already been made. And the person who made that argument was then and now CTO of Fastly, Tyler. So Tyler just pushed forward on this, and I built the first prototype, learned Rust to do so, embedded. CraneLift. There was not WASM time was kind of nascent at the time, so they built Lucet, which was a runtime around CraneLift. Yeah. And then as WASM time started to be used and in a lot of other scenarios, then they were able to merge those projects and kind of feed both of the optimizations from both into the same code base, which is now called WASM time. And so, that was a huge heavy lift. I mean, it was running a new ISA in a new kind of form factor, a very serverless sort of factor, as opposed to the usual like container kind of style of serverful. And then, alongside this battle tested, Varnish VCL kind of engine. So it was a huge amount of work for everyone.
Yeah. What do you think the biggest barrier that was experienced in creating a multi-tenant service like Fastly Compute out of WebAssembly, which WebAssembly is still growing, it's still coming into its own. Right. What's the biggest the problem there?
Well, I guess it would probably be split between two things. One is Fastly had to stand up all its own SDKs for all the languages because the ABI was not WASI. It was Fastly specific because there was no WASI HTTP then. So a whole bunch of SDK work, which is kind of motivation for how can we factor out a lot of that work and share that across the ecosystem. That was one part, and then the other part was just capacity management, quotas, and running this at scale, not letting guests overtake the CPU. Quotas in all the right places, which is not a thing that you get for free with WASM. It's a thing that's very bespoke to like the context you're running it in. So some support for that's in WASM time, especially a lot more now, but a lot of it we just had to build out and tailor to like the particular situation we were embedding it in.
Yeah, that seems very similar to what we experienced with Oscar with Suborbital and also Matt with WebAssembly in Nginx Unit as well. That's great.
Yeah,
Now we're ticking down to the end here, but I thought I'd give you a moment here to just tell us what else you're excited about. It doesn't even have to be in the world of WebAssembly. Is there something you've spotted out there that you think is really cool that's going on?
Oh, I mean, so much. Let's see. Let's say I mean, a lot of the things I'm excited about are WASM adjacent. I'm always, just because it's so
Get
far away
that.
from what I work on, I'm excited to see WASM in database use. I think there's a lot of cool opportunities treating WASM as a UDF, user-defined
Yeah.
function, and that really speaks to some of the in a user-defined function environment, you're really limiting the set of capabilities you're giving this WASM. You run to kind of be a pure function, right,
Mhm.
from data that's coming in from some tables, and it's going to go out into a table. And I think that's just it's both could provide huge value, but also like really showcase some of the unique properties of WASM.
That's really cool. With that, I think that's all the time we have for today, unfortunately. Luke, thank you. Big thank you to you. Great
Thanks for
discussion.
having me. This is
And
great
as
chance.
always, Oscar and Matt, thank you very much. It's a big application world out there. It's time to unleash the power and promise of WebAssembly. And so for Luke, Matt, Oscar, and myself, thank you for listening in, and be sure to hit that subscribe button for future WebAssembly news and views. Take care.
That's a wrap for our WebAssembly adventure, fellow code explorers. Thanks for joining us. And until next time, may WASM be with you.